So we have the first circuit wired up. In fact, I have all of them wired up, but I must get something wrong. One of them stopped working. So we'll probably try to troubleshoot it. So figure 14.2, 14.1, very simple circuit. So here it is right here. Here's my 2N3904. Here's my 2N39. I'm sorry. This is my 2N3906. This is my 2N3904. The 2N3906, of course, is the PNP, right? The 2N3904 is the NPN. Notice I have them facing each other because the emitters have to be connected together. Here's the 330 ohm output. This black wire right here is jumping the bases together. The red wire is bringing in plus 9 volts, and then the blue wire, wherever it went, blue wire is bringing in the minus 9 volts. Y'all see it? We okay? So real simple circuit, huh? Yeah, 41-2. Notice we're not bringing in a coupling capacitor. We have these things wired class B, but they're not really a good class B because there's no bias on these transistors at all, right? Except for the power supply voltages connected, because there's no base bias at all. So these guys here are biased off, right? You understand that? Because, so what turns them on? So what turns them on? We don't bias them on. What turns them on? So what's turning them on? What's turning them on, guys? Should be pretty obvious. I'm looking at the same schematic y'all looking at. And I look on the left and I see this symbol with a circle that's got a sine wave signal on it, right? It's putting out a voltage, right? You understand that? So when the voltage gets up above 0.7 of a volt, it's going to turn on the what? Positive 0.7 of a volt. Which one is it going to turn on? Okay, the NPN, right? Okay. And then when it gets down to negative 0.7 of a volt, it's going to turn on what? Okay. And then, of course, this is common collector, so whatever's on the input is going to be passed through to the output. So these are common collectors, but we have it ranged in what we call a push-pull or class AB arrangement. Are you okay? Yes or no? So when we look at the output signal, swing my camera around. It raise it up. So this is the output signal. Of course, the blue can never get as big as the yellow anymore because of turning the transistor on. But what we get is we get this little problem right here. And we call that crossover distortion. What's causing the crossover distortion? Well, not even when we get to 0. It takes about 0.7 of a volt to turn them on. So when this thing drops down to about 0.7 of a volt, whether it's negative or positive, the transistor is going to turn off. And then it's going to wait. So we got a 1.4 volt gap there where the transistors are literally off. Y'all understand that? They are not literally off, they are off. So we create what we call a crossover distortion, which is this guy's right here. Y'all understand that? So we have it hooked up. Let's see what it's asking us to do. It's asking us to draw the output waveform on figure 14.1. Why it don't look real good right here, I don't know. It just messed up on me, so I don't know exactly what's going on. So got minus going to collector, got just going to that. Yeah, this is doing something funky right here. This is what it's supposed to look like right there. I don't know what's going on right here. And of course you need to draw a whole cycle, right? But we can bring AC directly into the base, which is really, really neat. But we got to be, one thing we got to be cognitive of, if when we reverse bias Q2, we can't exceed the reverse bias breakover voltage on the base. Y'all know how much that is? Where would that information be at? Okay, so the data sheet. So we got to be careful with this guy. Since we're direct coupling into it, we've got to be, and y'all got them on Blackboard. I'm going to look for them on our, and of course the 39, and these two transistors need to be matched pairs, what we call complementary pairs. And what does that mean? They're the same data sheet, but one of them's for positive and one of them's for negative, right? I mean, one of them's for an NPN, one of them's for a PNP. So this is the data sheet on 3904. Yeah, well, what we're trying to do is we're trying to get both of them to turn on and turn off at the same time. The only way you can get them to turn on and turn off at the same time and have the same gain, then you need to have what we call a matched pair, which means they have to have pretty close to the same beta. We know that's kind of, but they've got to have the same breakover voltages. So these are all breakover voltages right here. So these are reverse bias. So here's our breakover voltage collector to emitter. So right off the bat, that means we can't turn this transistor off with more than 40 volts across it. If we try to turn it off with more than 40 volts across it, it could break over. And if it breaks over, what's going to happen? It's going to mess up the transistor, right? You understand? This is the breakover voltage collector to base, which for some reason is a lot higher. But here's the breakover voltage of emitter to base. So this is reverse bias. So if we get over 6 volts on this thing, it could do what? It could mess it up, right? Base to emitter. Now if we came over here and looked at it on the 3906, it should be the same, hopefully. Same package that we're using here. Okay, so this says it has a breakover voltage of 5 volts. But see, there's the 40 volts, there's the 5 volts, the other one is rated at 60. And look, the minimum beta on it's 30, the maximum beta is on at 300. That's exactly what the 3904 was. So that means what we're doing is we're using a matched pair. So they basically have the same characteristics, right? So they should turn on at the same time. The base should be about the same on both of them. You know, are we okay?
Say turn on at the same time, is it more like how is it?
They are on at the same time, but it's what we call a push-pull. So what happens and that's not exactly true. This is what we call a complementary amplifier. A push-pull amplifier is a little different. On a push-pull amplifier, they're both of them usually always on, and I'll show y'all that in y'all's lab. These are two Class B amplifiers. So they're only on for how long? Well, they're not quite Class B. If they was Class B, what would we expect? Or are these Class B? Is this 180 degrees? Huh? Yeah, it is clipped. So no, it's not 180 degrees. So these would probably be classified C's or very low C's. They're almost Class B's, but they're not, because we've got to do something to make the input signal turn the transistor on, but we want the base to be setting at 6 or 7 tenths of a volt, right? You understand that? If it's setting at exactly 7 tenths, that means there's 0 volts on the emitter. If there's 0 volts on the emitter, right, you understand, then there's no current flow. Now, if we put an emitter resistor in there, then we could have, 3 volts on the base, and we'd have 2.7 volts on the emitter, and then we run that through a resistor, and we have an emitter current, right? You understand that? So we got to get an emitter current. So if we're going to put an input directly in on the base, we're going to have some resistor. On a common emitter, we put that resistor over there on the emitter, right? You understand? Are we okay? Everybody okay? So let's look at the next one. Y'all got the diagram drawn? So we got to measure this. I'm sorry. No, that we don't have. Remove power from the circuit, compute the parameters, the DC emitter, assume 7 tenths of a volt drop in base. Okay, is this table 2 for this circuit? So what is 41, what does 41.2 go with? Okay, so these tables go with it. But what would I expect if I come over here and measure the AC, the DC base voltage on this amplifier? What would you expect it to measure for the figure that we have constructed right now? Huh? 0. Okay. So let's change the angle of my meter. And so I'm going to measure on the base, which is right here. Okay, see, it's measuring 0, right? And then, of course, if I go to the collector, this is the collector on this one. It's measuring -9. That's the PNP. And then here's the NPN. It's measured +9. But the base measures 0. I'm putting AC on it, but remember, the DC average of an AC waveform is what? 0. And that's why the meter measures 0. Okay, so what we got over here, and something's going on, we'll have to figure out what's going on. So let's move on to the next thing. Can y'all see how this guy here works? And we're going to modify this next. So we come over here and we have a so we have a 10K resistor right there. They're calling some R. Then I have a diode. Then I have another diode. And then I have a 10K resistor right here. So up here we have +9. Right here we have, I put a comma there. I shouldn't have done that. I messed up. Down here we have a -9. So if I came over here and took my meter and went between common, okay, which is common to both these power supplies, and I took my voltmeter and measured right there, what would it measure? Well, let's leave the diodes out, and just to do it real fast, what we'll do is I'm going to come over here and I'm going to put two resistors, because everything matches, right? You understand that? And for some reason, I don't know why students has problems seeing this. This is one of those things that's just as clear as day in your mind, and then it's hard to explain. So let's say this is a 1K, right? And this is plus 10. And this is minus, this is 1K, and this is a minus 10. Well, what's the difference in potential between there? Between a plus and minus 10. What's the difference in potential? Huh? 20 volts. Okay. So 20 volts. We got to drop 20 volts in the circuit. Okay? 20 volts in the circuit. How much is the 1K, each 1K going to drop? Huh? Okay, but I want the value. You're right, the same. But how much are they going to drop? I got 20 volts applied to the circuit. How much is each one of them going to drop? Okay, 10 volts. So this guy's going to drop 10 volts. 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 What's the voltage right here in the center going to be? Huh? 0 volts. That's going to be 0 volts right there. So if I measure between these two diodes, what's it going to measure? It's going to measure 0 volts if everything's okay. Y'all understand that? Which is pretty neat. So I've got this transistor connected right there. Okay. And this goes directly to plus 9. Then I've got this other transistor connected right there. The emitters are connected together. I should have drawn them a little closer together, but we'll connect them like this. And this is connected to minus 9. So what would the voltage be right here? Is the diode forward biased? 0 volts plus 9. It's not going to be plus 9. 0, so this is 0 volts, what we called it a virtual ground, but it's not a ground. It's not a ground, right? But it appears to be what? Ground. It's going to measure 0, so it appears to be a ground, but it's not. So this is 0 volts. There's plus 9. There's 0 volts. What will we measure right there? .7 volts. What will we measure right down here? Minus 0.7 volts. What would I measure right here? I measure 0 volts. So the transistor is not on, but it's right on the what? Right on the cliff of doing what? Turning on. Okay, so that means my input signal is not going to actually turn it. When it turns the transistor on, the 0.7 of a volt has already been taken out by the bias. So what we'll do now is we'll come up here and we'll put our AC signal in right here. So we put our AC signal in right between the two diodes. Right here. So we'll come up, still don't have to use a coupling capacitor, right? So we bring our AC signal in right here, or whatever we're trying to amplify, put it right there. And what we'll get out of here, when it goes positive, this guy's ready to be turned on, right? Is what? It's an NPN. It's ready to get turned on. What's it going to do? It's going to turn on. Then we get down through here. Then what's going to happen? This guy right here is going to do what? Turn off. And what's going to happen? And what are we going to get rid of? Yeah, the crossover distortion. We don't call it clipping, because literally clipping would be if I came up here and something happened like that. So if we cut off the tops or we cut off the bottoms, we call that clipping. So this is what we refer to as, the other one's what we refer to as crossover distortion. That's when we come over here and we see this, and we see this, and that's what happens. But putting those two diodes in there and setting up a bias, we're still extremely efficient, right? You understand that? But we've done away with our what? Crossover distortion. So this was working, guys. We're going to come up here and we're going to troubleshoot this. So this is the second circuit we have hooked up right here. And what we're going to try to do, what happens when I tried to add the common emitter amplifier. So here we connected the two transistors together. So we connected the emitters together. Couldn't do it right here because of the bias. So the red line up here, this is my +9. The blue line, got to be real careful because if these two guys touch together, we got a short circuit. This is my -9. So this is my 10K that's going from the +9. It's going down to the base. Here's my 2N3904. Here's my 914, which is a small signal diode. We don't need these guys to handle a lot of current, so they don't have to be a high current diode. A very small diode because all they're doing is handling that bias, right? Then this is the other 2N3904. So we see this. So this has the anode pointing toward the base. This has the anode pointing toward the other cathode. Then this goes into the base. And here's my other 10K right here. And so if I come up here with my voltmeter, if I got all my grounds, and I measure to the base, what should I measure? If I measure between these two diodes right here, what should it measure? Should it measure what? 0. Okay, so see that? So one of the diodes is not slight the same. That's 6 millivolts, right? 60 millivolts. Are we okay? The problem is, so what I'm going to do is I'm going to take my input signal that's right here. It fell off. And where do I need to put my input signal at? I'm listening. So where does my input go? I get my scope. Okay, guys, where do I need to put this at? Where does my input go? Okay, between the two diodes. So we'll hook it up here. Okay. This is my input. Let me turn it downward. Okay, so there's my input. Oops. And here's my output. So what's the problem? That's not saturation, that's cutoff. If I was saturating my NPN, then the top would be clipped. If I was saturating my PNP, my bottom would be clipped. If it's in the 0, that means this is class B. It means that transistor's not doing what? Huh? Okay, the only time we use saturation, but we're talking about an AC sine wave. Okay, understand. And so don't get it confused with a common emitter amplifier where it's a class A amplifier. These are not class A amplifiers. These are class B amplifiers. Right? You understand. one of them turns on with a negative, one of them turns on with a positive. So what that means is, if I come over here, so if I was looking at the output, and the output did this, that would mean the NPN is saturated. If I'd come over here and looked at this, that means the PNP is saturated. Okay, you understand that? That's what we call clipping. We're not looking at clipping here. We're looking at this. So all we've got 0 volts, and then we got this, right? Right. And then we got 0 volts, and then we got that. So what's the problem? That's not saturation. So I'm missing that whole alternation right there. Y'all understand? So what's the problem? Huh? The PNP's giving me the negative. The negative's fine, right? I mean, if I look at this output, the PNP's fine. The PNP's doing exactly what it wants to do. It turns on, gives us this alternation right there. So what's going on? So what's wrong? Come on, guys. Huh?
Cuts off.
Well, you're not saying it cuts off. If it cuts off, I would see something, right? It's never what? Yes, it is cut off. You can't say it cuts off, because if it cuts off, it had to be what? It had to be on. It's never turning on. This sucker's cut off. So what could be the problem? What's the first thing I would probably check? I would check the power supply, right? So first of all, I'll look at it visually to see if I've got any problems, and I don't see any. So what I'm going to do is I'm going to come over here and I'm going to look at the collector. Sorry guys, this is why they sell these resistors so cheap, so they don't make the leads near as thick as they used to. They're real thin leads, so they pull out real easy. So I need to find the emitters. So there's the emitters. Run this over to the negative. So what we're going to do is we're going to come over here and I'm going to look at the collector. So I'm going to look at the collector of my NPN. Here's my NPN right here. I'm going to look at the collector. What should be on the collector? What's supposed to be on the collector of the NPN? What's that? 9 volts. Okay, so it's got 9 volts on the collector. Huh? The base, what should the base have on it? Not anymore. A while ago it was 0, right? But the problem was, that's why we had crossover distortion, because the bases were at 0. Okay. So what did we put up there a while ago? Let me find the PowerPoint. What should be here? And what should be here? Okay. So I'm going to come up here and look at the base. Oops. So that's the base. Is that good? Okay. So what do I need to look at now? $39.06 is working. 39.6 is working fine. I know my problem's not down in the 3906, right? Because it's doing what it's supposed to do. My problem's somewhere up with the 3904. Understand? Yes or no? Huh? I mean, I've taken my iPod off. So let me, my scope will pull that out. So here's my input sine wave. There's my output. Where does the negative come from? Which transistor? The 3906. So 3906 is working fine. But we're not going to look at that. We know the minus voltage has to be there. If the minus voltage wasn't there, we wouldn't be getting. But something's going on with the 3904. So what else do I need to look at? So the base is setting at 0.7 of a volt. The collector's setting at plus 9 volts. What do I need to do now? Well, I'm going to take my scope and see if the base is getting the right voltage. I'm going to come up here now. So we're to the point where we need a scope. And there it is right there. Yeah, so this is what's on the base. So we got collector voltage. The base is setting at 0.7 of a volt, which is where it's supposed to. The signal's getting to the base. What do I need to try now? Let's look at the collector real quick. Yeah, collector's dead. So what do we think we need to do? Yeah, we're going to pop the transistor out and check to see. If I was screwing around up here, I might have bopped the thing. So we'll pull it out, put our meter on what scale? Yeah, put it on the diode scale. This is an NPN, so I'm going to go ahead and put my positive right here. I'm going to go to my emitter. Emitter looks okay. Go to the collector. Oh, can y'all see my readings? So here's the collector. I got it backwards. Collectors, so I've got it backwards, so the collector is going to be on the right. So is that good or bad? Huh? 0.6 of a volt, 6.6 volts. Is that good or bad? Between the base and the collector, is that good or bad? Oops, slipped off, guys. Is that good or bad? Huh? This is the base and the collector. Is this good or bad? Y'all did labs, guys. Y'all check this out. Is this good or bad? Huh? Of course, I'm doing this so y'all know y'all wrong, right? If you look, and now this is not the way it works. Remember, this is an NPN. So if you think of it like this, then that's basically what we're doing when we check a meter. Okay, so that means an NPN. Okay, I was putting my positive on the base. I was putting my negative on the collector. Is that forward bias in that junction? Huh? Yes or no? Yes or no? Okay, yes. Y'all understand that? N negative, P positive, and and it's silicon, so what should we expect? Yeah, about 0.7 or 700 millivolts. It's measuring 6.66. Is that good or bad? Huh?
0.66.
Yeah. Is 0.66 good or bad? It's very good. That 7/10 of a vote is an approximation. It's 0.66 votes, approximately 7/10 of a vote. Yeah, that's good. That's really good. There's nothing wrong with that. What do I do with my transistor? Okay. Are you okay now? I mean, that's even been on test, guys. I don't know. Do I scare y'all or something? Huh? Well, I would rather you give me the wrong answer than not give me an answer at all. Okay, so here's emitter to collector. And don't say that's about, that is really good. That is a good transistor. Okay, that's a good junction. Okay, now I'm going to take this negative and I'm going to move over here to the emitter. Is that good or bad? That is bad. Okay, so is the transistor good or bad? It's bad. So why am I losing my positive alternation? Because Rick screwed up the transistor somehow. Power's off. We'll check this one too, just to make sure, because this is one we burn up. Hey. Okay. All right, thank you. This is the one we heated up and cooled down, and the soldering iron touched it a little bit. But so here's the base. I got positive on the base. Okay. Here's the emitter. Good or bad? Okay. Here's the collector. Good or bad? Good. Always go in and check emitter to collector. Okay, so we expect this to be an open, right? This is emitter to collector. So this transistor right here looks great. Go plug it in. So undoubtedly I touched the power supply on there or something, I don't know. Congratulations, guys. What's missing now? There's no distortion. So see what we're doing with those two diodes is we're what? We're not turning it on, but we're getting it right on the point of being turned on. So that's what the purpose of those two diodes are. Really neat, huh? A buffer would be what we call a go-between. What it does is, normally we use buffers to protect things. It's just, well, all these guys are just a bias circuit. It's just that what we're doing in the common emitter, when it was running in Class A, we had to bias that thing on. Right? You understand? What we're doing here, we're biasing it at the verge of being what? On. I mean, we're putting it right at the verge, but they're not on. So if we look, even now, if I come over here and look at the emitter, if it's biased right now, to be perfectly biased, of course, these two resistors would have to be exactly right, and the VF of these two diodes would have to be exactly right. But what we'll do is we'll come over here and we'll look at the DC on the emitter. And if I look at the DC on the emitter, oops, I pulled out my load resistor, guys. What I'm going to do is I'm going to hook the scope probe up to a wire so the scope probe is not loading. Okay. So here's our output right here. Right there. So the problem is the weight of the scope probe keeps unplugging it, pulling the load out. So I'm gonna put a resistor. I'm gonna put a wire on here. Okay. If I measure the bias voltage, if I measure the output voltage DC, how much? What's it gonna measure? Let me hook my black lead back up to me. Okay, so I'm gonna measure the bias voltage on the output. Well, what should we expect it to measure? Yeah, it should measure pretty close to 0. So we've got 90 millivolts. So it's not perfect. Why is it not perfect? Well, our components are not perfect. So if I look at the bias on my PNP, my NPN, we see it's setting almost perfect. But when I look at the bias on my NPN, on my PNP, it's -5. So what the problem is we don't have these things biased perfect, but they look real good. I mean, look at the output. That's pretty neat, right? No gain. Why no gain? Well, it's no gain because we've got we get no voltage gain because it's common collector. And what does common collector give us? What kind of gain does it give us? We know we get power gain. So we get power gain, but how do we get power gain? Current gain. So common collector gives us a current gain. So if you look at the schematic, we got a 300 ohm on 330 ohm on the output. Each one of these transistors is seeing that as a 33K. So the input impedance would be 33K. The output impedance is going to be 330 ohms. So the input impedance, the function generators basically provide almost no current at all. Y'all understand why the input is 33K? You say, well, I don't see an input resistor. Well, my input circuit is here now. Comes through here. Input comes through. Positives go this way, go out this way, and go through that resistor, which is a 30, our ratio, 330 ohms. Anytime we go through here, it's times beta. That resistor over there is seen as times beta. This is a 330 ohm, so that'd be 330. Typical beta for this is really, really good, is 100. And of course, when the negative comes through, the negative signal comes through and turns the transistor on, right? Same circuit, but it flows like that through the 330 ohms. So my function generator is seeing almost 33K. My load is 30 ohms. So we could calculate the current, well, we'd have to get the voltage. But you can see the input current is going to be a lot less than the what? The output current, even though the voltage is the same. So this source over here, our signal source is almost providing hardly no current, but we're getting a lot more current on our output. That makes sense. Remember, once these transistors turned on, that emitter resistor, if we don't bypass that emitter resistor, then it's seen as times beta. And we never bypass the load resistor on a common collector amplifier. So you'll never see a common collector with that. You'll see that on a common emitter, which lowers the input impedance, but it increases the gain, right? You understand? So about what current gain should we expect? Current gain? I hope not. We get a current gain of slightly less than 1 out of a common base. This is not a common base. And that's what we just got through saying, right? What do we get out of a common collector? We get a current gain. So what's the current gain, guys? It's going to be 33K divided by 330. I mean 330, Rich. So we're getting 100 current gain out of this. So what power gain are we getting? Yeah, so power gain is going to be equal to 100 also. How many dB would that be? It's going to be 20 dB. Because 100 is 10 to 10 to the second, right? You'll understand that. dB is the power of 10 raised to multiplied by 10. So 10 to the second, right? Times 10 would be 20. So this is 20 dB we get out of this thing, which is pretty good. Okay, so what we do next? What's the next circuit? And this might work now. This is where I screwed up right here, trying to rearrange it. Okay, so let's make our measurements. I'm sorry. So let me go back to the camera and bring our meter up. Okay, can y'all see it? So what measurements do we need to make? VE, we expect it to be 0. So here's VE right here. And it's measuring 92 millivolts or 90 millivolts. Not bad. VB1, we measured that a while ago. So here's VB1. Yes. Oops, sorry, came off, guys. Now 690 something, 697 millivolts. Here is VB2. So I'm looking at the other side of this guy right here. So here's VB2. It's minus 500 millivolts. And what about ICQ? What do they want there? The current in onward is defined by applying Ohm's law. Well, where do we need to calculate the current? So R1 is going to be dropping, should drop around 9.3 volts, right? So estimated it's going to be 930 microamps. What's ICQ? This current is ideally I guess that means a quiescent current. So what's our current going to be? They're calling it I1, but what they're trying to do is calculate the current. And now we know the voltage drop of this guy right here is what? 9.3 volts. Everybody understand that? Because this right here should be virtual 0. So R1 is going to be equal to what? It's going to be equal to 9.3 calculated over 10K, which gives us what? 930 microamps, right? So what should ID1 be? And then what should ID2 be? And what should what's this guy down here? R2 be? Huh? That's fine. They're going to be a little different, but we're going to lose base current, right? But, we're not going to lose base current because base current is zero, right? Because we're biasing these things right. So these guys, they should be pretty dang close. Yeah, so that's a series circuit. So that's what they're talking about. ICQ computed should be 930 micrograms. So it takes only 930 micrograms to bias this sucker on. Right? Does that make sense? Oh, the input impedance wouldn't be 33K, by the way. We screwed up. I screwed up. Can y'all see my problem? So here comes the input. Then we hit this dot right here. What does that mean? It means parallel, right? So that means some of it's going to go this way, back to the 9-volt supply. When we turn on the negative transistor, it's going to do the same thing. It's going to come over here. See that dot? So that means we got a parallel circuit. So let's recalculate that. I'm sorry I messed up. So that would be, so Rn would be equal to 1 over 10K plus 1 over 33K, right? Y'all understand that? Everybody okay? Huh? Yes or no? Yeah, we're kind of ignoring the diode because the diode has, once it's turned on. So what we got? So I'll let me get by with that. So that's y'all's fault. So AI would be equal to Z out over, Z in over Z out. So what's our input impedance? Less than 10K. 7.7K. Thank you. And then our output is 330 ohms. 330. I don't know why I'm doing that. So that's going to drop our gain down a pretty good deal. So what's our gain? What's that? 23. And how many dB would that be? So I don't know. I can't do that in my head. So dB would be equal to the log of 23, right? So what's the log of 23? And then we multiply that times 20. Are we sure we're right? So the log of 23? Log of 23 is 1.36 times 20. Not times 20, guys. That's a good job. I know what I'm doing, believe that or not. So what's the power gain? That's what we're looking at. So what's the power gain? So what's AI? 23. Okay, so what's power gain? 23. So when we're dealing with power, what's the formula? It's the log of 23 times 10. How did I know that was wrong? Because a while ago when we had 100 power gain, it was 20 dB, and we're saying we got 23 dB, and it's going to be a 23 power gain, and it's going to be more than what we had when we had 100. So what is it? 13 point? So y'all understand why I knew that we were doing something wrong? Because a while ago it was obvious because we had a power gain of 100. And I know that 10 squared is 100. I multiply that by 10, that would be a power gain of 20. Well, here we had a power gain of 23, and we were trying to say we had more dB than when we had the power gain of 100. So 13.6 dB. And the gain has no. Okay, so what else do we need to measure? We need to compute VP out. So what are we putting in? So I'm gonna set this up so we can do this a little easier. So right now I've got it on 2 volts per division, 2468. So let's adjust it down just a hair, and I'll put the scope back up there. Okay, so here's my input, and y'all can't see the divisions. You have to see where it now, right? So I have it on 2 volts per division. So here's channel 1. So you can see the 2 volts real good if I don't get my finger in there and cause my camera to get out of focus. Boy, it was focused good while ago. Okay, there we go. So how many volts we got coming in? Got 8 volts coming in. Okay. So what should we expect on the output? 8, right? AB. So I'm gonna come up here and bring channel 2 back up. My scope pro came off. Hold on. Okay. I thought when I moved it, it clipped it, but it's not clipped. It's me moving. Now notice now the output is equal to the input. Last time when we did a common collector, the output was slightly less, right? But here we're biasing these things right at on, right? So look at that. Ain't that neat? So how many does it measure? Yeah, it measures 8. So that's what we put in. That's what we expected out. So IP, what's IP? Lowercase. So that's AC current. So in these labs, if we see uppercase subscripts, it means they're talking about DC. If we see lowercase subscripts, it means they're talking about what? AC. So how much current how much AC current are we anticipating in that 330 ohm resistor? I is equal to so let's do it a different way. How much would we measure if I put my ammeter in there? So let's do RMS current. So we got 8 volts peak to peak. Okay, what's the first thing I'm supposed to do? Convert this to RMS. What would that be, RMS? Right, guys. What would that be, RMS? Huh? They're giving me a heart attack, guys. This is peak to peak. When we deal with RMS, we're dealing with V peak. So that's going to be 4 times 0.707. 2.83, or 2.8 volts is good enough. So I know what y'all did. What'd y'all do? Used 8, right? But remember, your scope measures peak to peak. When we do our formulas, it's the average. It's the effective voltage of an alternation. So yeah, 2.8 volts. So what should be our measured current? Our computed current, which would be the same thing if we measure. No, guys, what they're asking for. So let's do the peak and fill that in. And what I'm going to do is I'm going to measure this with my ammeter is what I want to do, and just to make sure, just to show you how good this is. So the lab is, and I'm going to use when I grade this, by the way, I'm going to use a grade sheet. So we need to do. I'm going to use the key. So we need to do it what the thing asking for. So what type of current is it asking for? Is it asking for RMS or peak? Well, we'll do RMS so we can measure it to see how good we are. So I peak would be, and this is out, would be equal to 8 divided by 330 ohms, right? And then P out, and this would be peak. Here they don't say peak, but we'll do it both ways. So peak out, peak out, or AC would be equal to I peak out times V peak out. V peak peak. Yeah, peak. They're asking for peak. Now why they're doing that, I don't know. So that's not going to be 8. That's going to be what? 4. Thank you. And that's going to be V peak out here. So what do we come up with? So V out, V peak out would be equal to, what's this right here? Huh? 4 divided by 330. 12.12 milli or 12.1 milli times V peak, which would be 4. What does that give us? 48.4 milliwatts. And this would be watts, by the way, because this is all resistors, right? Let's do it. So let's do it the other way. So P out would be equal to 2.8 squared divided by 330. What does that give us? What's that? 23.8 milliwatts. Now this right here is RMS, right? You understand? Y'all understand this formula right here? That's one of our power formulas, V squared over R. This right here would be peak power. And which one will we really be concerned with? This is the guy we're concerned with because that's how much work we're actually getting. So let's measure our current. So what should we be expecting? We should be expecting, what was the first one we came up with? No, so I would be equal to 2.8 divided by 330. Y'all understand this? Because what's this voltage right here? RMS. And what is RMS? What is it? I know what it stands for, but what is it? We call it what voltage? What do we call that? Anybody remember? We call that the effective voltage. So this is the work we get. So this is the work we're going to get right here. The book's calling out this guy right here, which basically doesn't mean anything. This is the guy right here that we're interested in. And this would be the current that we're interested in too. So what's our RMS current? Which is what my meter's going to measure. So I'm going to set my meter up to measure current. Oops. I'm going to put jumper plugs on it to make it easier. Jumper. I'm going to take out my input. I need to put my meter on AC amps. What do we calculate? Then see how we're going to do this. Where's my output at? This is below. Right now I'm measuring 0. Okay, remember when we're measuring current, we don't measure across anything, right? I measured 8.1 milliamps. What did we calculate? Huh? That's not too bad, is it? And that's RMS, right? Okay, guys, y'all go ahead and take a break. We'll come back. In this section, I've calculated it out for you, but we'll show y'all how we get this thing started. And you already know enough to calculate this whole thing, believe it or not. It looks intimidating, don't it? But where are we going to start at on this guy? I know one voltage already. If everything is biased correctly, I know what that voltage should be right there. Should be 0. So we can start right there. Right? Okay. So what we have here is we have a common emitter. So this is a two-stage amplifier. So this is a common emitter. And what do we get out of a common emitter? What type of gains? Voltage and current. Of course, all of them gives us power gains, right? So, but we can't get a lot of current drive out of these things because they got a high output impedance. So we got a common emitter. How do I know it's a common emitter? Because I'm inputting on the base. I'm outputting on the collector. So the emitter has to be common. Right? You understand that? Yes or no? So that common emitter is going to give, and we don't have the emitter resistor bypass, so it's going to have a pretty good input impedance. It's not going to load it down. But we might feed this from another amplifier. But this would actually be the actual output. So we could get a little bit of work out of this two-stage amplifier. Okay. So I know that's 0. Everybody follow me so far? So what would we have? We know this is 0. That's virtual 0. So we know this is going to be plus 0.7. This right here should be minus 0.7. I know R1 should drop 9.3 volts. So IR1 is going to be equal to 9.3 divided by 10K. And we already know that's going to be 930 microamps, right? We've already calculated that. Are we okay? Okay. I have no idea what the resistance of the transistor is. It's a dynamic resistance anyway. But I do know this right here is a series circuit. So I know this is a series circuit. So I know the current through R1 is going to be the current flow through R2. So I can calculate VR2. So VR2 is going to be equal to 2.7K times 930 microamps. Is that, no, I'm not 4, that's not 2, that's 4, I'm sorry. I can't read this. VR4. So what's VR4 going to equal to? Wait, guys. Wait, guys. What's that?
2.5K.
Maybe 2.5 volts. That's microamps. Yeah, see what you did wrong? Okay, so what we need to do is we need to find out this is Q3, so we need the emitter voltage VEQ3. So what's the emitter voltage going to be on Q3? I know what the emitter voltage on Q1, because if I don't know the emitter voltage on Q4, I mean on Q3, I cannot know the base. I can't figure out what the base voltage should be. So what should VEQ3 equal? Anybody got any ideas?
You said it-
I'm gonna agree with that. It's not right. Because that resistor drops 2.5 volts. So you got to remember when we take these measurements right here, these are relative to common. So what I say, if I come over here, I got -9. I come over here, I've got something that's going to be 2.5 volts more positive, right? You'll understand that. And that's the big problem people have. They see a voltage drop across the resistor, and we're not asking for the voltage drop across the resistor. I'm asking what's that, what I would measure at the emitter of Q4. So this is going to be a -9 minus a minus 2.5. So we change the signs and add, right? So what we're going to have there, well, if we measure that, what should we have there? All the math is there for you guys. Minus 6.8. No, not. Minus 6.5. How did I come up with 6.8? I came up with 2.2 volts. Is this current up here right in my math? What did I come up with the current? I got 830 microamps. Y'all got 930.
and what, 8.3 volts.
Oh, that's what yeah. Sorry guys, I didn't. Y'all let me get by with murder up here. What's the voltage? What voltage do we have applied? Yeah, +9. So there's no way in the world that could be, so let's redo that. I don't know why I didn't, because I was thinking about the last circuit's what it was. So this guy's going to be 8.7 volts, right? Is that what I put there? 8.3. Oh, 8.3. It is 8.3. Y'all understand what I did? So it's like the blind leading the blind. So this should be what? 830, yeah. And I should have caught that, guys. I'm sorry. Y'all like it when I make mistakes, right? And that's what it was a while ago. A while ago, though, we had 10 volts applied. No, we had 9 volts applied. So I screwed up a while ago, too. So this guy here is going to drop 8.3. So that means this guy here is going to drop less. 2.5K times, yeah, 2.7K times 830 microamps. What's that going to be? Yeah, 2.2. And so what should we have right here? So 9 volts minus 2.2 volts, Rich. Should have about 9.8, I mean 6.8. So I've got a minus 6.8 right here. What would I have right here? What we're looking for is dB Q3. Yeah, it's going to be a minus 6.1 though, right? Because we got a minus 6.8 right here. This guy's got to be 0.7 of a volt more positive than minus 6.8. So this is going to be minus 6.1. Everybody okay? Now, what we do to adjust this thing and compensate for everything is what we do is we come over here and we want 0 volts right there. Well, what sets that 0 volts is this right here. Well, what sets that is what this transistor's biased at. So that's why we have this pot. I'm not using a 5K. We don't have any 5Ks. I'm using a 10K. But it can be smaller. I mean, it can be bigger, but it can be smaller. Okay, that makes sense. I came over here and actually gave y'all how we calculate what we need to set that resistor at to get 6.1 volts. But all I did when I biased this, by the way, is you come over here and you put your meter right there, and you turn this pot until you get what out here? 0 volts. And that's what the purpose of that is. Because we want this to be 0, right? You understand that? And what we just did is we compensated for everything. This is going to be minus. So what I did when I set up my circuit, I just set this to minus 6.1, and you can see the bias turned out to be really, really well. So voltage gain is out over. Voltage gain is going to be hard to do. I actually did it there. But the voltage gain, we have to calculate the gain of the common emitter, emitter amplifier, and that came up to be a gain of 3.6. Now, we don't get a lot of gain because we did not bypass that resistor right there. And if we don't bypass RE in a common emitter amplifier, what does that give us? Gives us lower gain, but we get a higher input impedance, right? You understand that? So we don't get anything for anything, right? For nothing. So if we bypass it, we get more gain, but we lower our input impedance. And the lower your input impedance is, then the lower that this signal source right here is going to have to provide. So even on your antenna on your car, I guarantee you the first amplifier is an FET. So if you actually look at the schematics on the amplifier of your car radio, which is trying to pick up information off an antenna, right, you understand, antenna's got a pretty good input impedance, can't put out any signal, can't put out any power at all. So one of the big advantages of an FET is it almost got infinite input impedance, right, which means it's not going to load your antenna. So guys, this should be enough for us to calculate this. We should expect a gain of around 3, 3.6, 3.5. Not by this guy. This guy gives us no gain, but this guy right here is where we're getting our gain. You understand that? Are you okay? Okay, so what do we need to measure here? What do we need to measure on our chart? Okay, VB3. What are we expecting right that now? A minus what? Yeah, we're minus 6.1. Okay. VE3. So VE3, we're expected to be about a minus 6.8, right? Okay, that's what we expected. And then that current is going to be 830 microamps, which is what it should have been a while ago. So I made that same mistake twice. That's why I did it. I made it a while ago, so that's why I made it over here. So ICQ3 should be 830 microamps. And then our voltage gain, we should expect a voltage gain of around 3.6, right? And what we did is we figured out what we did to get the gain is we figured out the output impedance, right? And then we figured out the input impedance, and then we used the formula for the common emitter. Okay, guys, so let's bring up the camera. Let me put the meter so y'all can read it. Got it on volts. Got it on 40 volts. Which should be okay. So I need, what's the first measurement we need? VB3. So here's VB3. So by the way, I just had this circuit already hooked up over here if y'all didn't notice it. And what I did is I pulled the 10K resistor out over here and replaced it with the transistor. So it was pretty easy to hook up. So here's what we're measuring there. We expected what? Yeah, but what I did though, so this was kind of cheating a little bit. I went over here to my emitters. In fact, we can come over here. I can do a little better. So what I'm doing is I'm over here on my emitters right here. And what I'm going to do is I'm going to adjust this thing till it gets to as close to 0 as I can get it without going over. And it's kind of touchy with the 10K resistor. Whew, that looks pretty good. Okay, so what I'm going to do now is move over here and see what it is now. So this is, we computed, with that thing balanced, we computed 6.1. And what is it? 6.06 or 6.1. That's pretty good. Not bad, guys. Okay. Now we need to measure VE3. We're expecting this to be minus 6.8, right? Minus 6.72. So it looks like this guy is balanced almost perfect. ICQ, we're not going to measure that because we'd have to break up a bunch of stuff to measure that. We calculated it to be 830 microamps, right? I calculated a gain of 3.6. Here's my input and here's my output. So my input, I have it on 500 millivolts per division. So that'd be 0.5, 1, 0.52. So I'm putting 2 volts in. My output I have set on 1 volt per division. So I'm getting 1, 2, 3, 4, 5.5 volts out. So what's our gain? Yeah, 5.5 exactly. So what's our gain? 2 volts in, 5.5 volts out. We're getting less than what we computed, but there's a lot in this circuit. That's not bad. So 5.5 divided by 2 equals 2.75. That's the gain we're actually getting. Class, this is, we're using a common emitter and then a class AB, right? So this is a class AB and this is a class A. So what's the characteristics of class A? Class A amplifier. Huh? Now they got to be biased on, but what's the characteristic of a class A in general? They have to be biased on. That's why they're so inefficient. What's the characteristics of the class A? It amplifies 360 degrees of the input signal. So whatever you put on the input is what you're going to get on the output. But this is a common emitter. So one of the characteristics of a common emitter class A is that the input and the output are 180 degrees out of phase. So we get this phase shift between the input and the output because our main amplifier is a common emitter. But it's still a class A, right? You understand? Okay, y'all understand that? So the main characteristics of a class A, to get a class A, we got to bias it on, but that's not the characteristic of a class A. The characteristic of a class A amplifier is we get 360 degrees of whatever we put in. Except on a common emitter, it's a mirror image, right? You understand? It's 180 degrees out of phase. Now the output is not a class A. It's what we call a class AB. So what we're doing is we're using two class B amplifiers to act like a class A. Now, the problem with a class A, they're about 25% efficient, right? You understand that? Which means it takes a lot more power in than we get power out. Class Bs are 75% efficient. So anytime we're going to have to output a bunch of power, we're probably going to use at least class B. Or AD probably, right? You understand that? But to get all the voltage gain and to get all the gain, we're going to use class A amplifiers. So we'll come in with class A amplifiers, and then when it gets time to get all that power, we're going to use a what? ABs. Because they're, why? They're very efficient. Yeah, I had one of my amps that I had in my one of my amps that I finally took my stereo down, but my wife got tired of my loud music. But it had a switch on it where you could switch it between AB or A. So normally when you was listening to real low volumes and stuff like that, I'd switch it to A. And then when I wanted some sure enough power, I'd switch it to what? AB. A lot of people don't have any idea what that is. So this is a nice little amplifier. It's a two-stage amplifier. Y'all understand that? So we have two stages. We have a Class A common emitter, and it's feeding a Class AB common collector. Are you okay? All right, guys, y'all go ahead and take another break. So I've got two labs out of the way. We could have done this in one night, by the way, but they let y'all go so early. Huh? When I looked at, and I couldn't understand that because when I looked at they had dropped the rain percentage for this area down to 30%. We didn't even get any lightning, though, did we? And yet yesterday, guess what they did? Y'all had any classes yesterday? Yeah, they delayed the opening of Jefferson County schools until 10 p.m. and we came in, so we were here during. Of course, we didn't have any tornadoes. They were all kind of north of us, but that was what was so unusual. Okay, guys, y'all go ahead and take a break. Two labs. So y'all supposed to turn in one lab tonight, the common collector, and then this lab will be due when? Next Tuesday. Yeah, I'll.
You're like.
You understand? That's why they, you don't understand the standard. Yeah. You know, I won't know. You wouldn't want to 2 hour shift. Great. Yeah, they talk. Keep talking. You'll never know. Keep talking. He's talking. I'm listening.